Hi all, this is the first of several permafrost modules that we'll be working on related to permafrost and climate change and permafrost and ecosystem change. So today we're going to be looking at data from the McMurdo Dry Valley's Long-Term Ecological Research Group related to ecosystem response to climate change and some real newsworthy results that they got several years ago. And now we'll look at the continuing record of climate change in the McMurdo Dry Valleys region. So this is going to be Permafrost Module 1, so it's called PF1 module. And what are we going to do? We're going to do analysis of MCM LTR ecosystem response data. So the first thing I'm going to do, of course, is read in our data. And so to do that, we'll tell our where the data are. So we'll set our working directory. For me, that's going to be in my Dropbox folder. Dropbox modules. Of course, your modules are going to be someplace else. These are going to be in our permafrost modules and PF1. That's where all the good data live. All right. So we'll set the working directory, and then we'll actually import the data. So call it, maybe make this on a new line so you can see a little bit better. MCM data, that's McMurdo data. Better than just calling it like data or something like that. And read CSV. And what we will get is from the data folder in that home directory, the McMurdo synthesis data in CSV format. And a lot of these you'll see I'm sort of partially typing and then hitting tab just to finish the line and see what's there. So reading the data, double check that some nice time series data are there. Yep, bunch of years. These are years, and these go from January in the preceding year to February of the year of, for example, 1998. The reason for that, of course, is that summer in Antarctica is December, January, and February. It's Southern Hemisphere summer. So we don't want to have like, numbers in our time series that are like 1987, 1988. That's kind of cumbersome to deal with. So this is just a reminder that the year is of the January, February of that season. All right, so one more thing as we're setting up our data, we'll bring in some libraries we need. We'll need these later, but the library that we'll need is called Plotrix. So we'll bring that in. That should install. If you don't have it downloaded, remember you can find it over in the packages window. So let's take a look at this data. We'll just do a couple of very basic plots. And, again, one theme of this module is kind of getting used to copying and pasting your code, right? If you can do something once, you can do it multiple times quite easily just by changing up a couple of variables. So we'll make a plot. In this case, we'll plot the McMurdo data. And let's plot our Y here is going to be our mean December, January, February air temperature. And we're going to plot that on the Y, and now on the X, we'll plot the year. So that's MCM data. And then we want the year, January, February. This is going to be plotting temperature versus time. Temperature is continuous, so the type should probably be a line type. So we can do type equals and line, L for line. Our line type we'll set to 1, just a nice sort of smooth line. And we'll get some labels. Our X label is going to be year, time series data, showing a couple of years of temperature change in Antarctica. And then our Y label is going to be, Y lab, it's going to be, in this case, mean December, January, February, air temperature. And then if you're using a Mac keyboard, that Option K will make the little degree sign. Otherwise, you could use an asterisk. You could figure out the code symbol for degrees if you wanted. All right, so we'll run that line and look at that. We have pretty basic temperature that is setting, showing temperature over time, temperature on the y-axis, and year on the x-axis. But you know what? Since we actually have the data, let's show that data. because of course the lines are connecting the dots between measurements. So we can always add to our plot command using the points command. So even if we make a line plot like we did here, we can add points to that by using the points command, and that will add in points. And this follows the same basic format. Y is a function of X, right? Y tilde X. So our Y here is going to be our McMurdo data. And we actually want to show, again, the air temperature data as a function of time. They are MCM data DOJF. And our point character, PCH, you're going to set to 20. That's going to be some dots. So when we run that line 14, that will add in our points. Just makes a little tidier plot and really highlights, right, the actual annual measurements that go into this. So this is going as our plot of air temperature. We might want to make a similar kind of plot, but to show a different data type, right? In the Antarctic cold desert, the temperature is really a very strong function of incoming solar radiation, insolation. That's the watts per meter square of sunshine streaming down from the sun into the Antarctic during the summer months. So we can copy lines 13 and 14 and just paste them. And instead of having to write all that code again, we can just change a couple of variables, right? So instead of plotting air temperature, let's plot, we'll just delete the air temperature, and let's plot our mean shortwave radiation. That's watts per meter squared. It's going to be a line. We're going to have year as our x symbol, but of course now it's not air temperature, it's now incoming solar radiation. So we might call it mean December, January, February solar radiation in watts per meter squared. And then points, we want the same thing, right? We don't want to show temperature again. We want to show our insolation data. So we'll just change up air temperature and go. And again, you can either type this in manually or just delete up until that DJF and then hit tab and let R complete for you the solar radiation. So now when we run line 16 and 17, we get a new plot, right? We get our solar radiation plot versus time. Again, looking at these two plots, right, we see these are showing some kind of change with time between years, across decades. The temperature plot looks maybe a little bit different from the insolation plot, and we'll want to figure that out. You know, what is this relationship between temperature and insolation? But then also what we want to figure out over the course of this whole exercise is what is it that is changing about the environment in the McMurdo dry valleys of Antarctica, and how is the ecosystem responding? So if we want to start looking at the ecosystem response, you know, maybe we should look at what's going on, for example, in the lakes. So the ice cover on Lake Bonny, one of the large lakes in Taylor Valley. So again, we can go and plot up just, you know, doing a little perusal of this data again. We'll get rid of our insolation plot. And now let's look at, for example, East Lobe Bonny ice thickness. So there'll be ELB ice thickness in meters as a function of time again. Nothing is changing about this except for our Y value and of course our label. So now we want to change that up from mean summertime insolation to now East Lobe Bonny. So East Lobe of Lake Bonny. And that's going to be ice cover thickness. And then again, that's going to be in units of meters, and we want to show off the data, so we'll make those points. All right, we run those lines, and one thing you might notice is not every year have these measurements been made, right? There's a little gap in the record. There's an early start in the 80s and 90s, and then a couple of years when the team either couldn't get out there or the benchmark was damaged, something was going on where that the data set is not reported. So we have, again, change in the thickness of the ice cover, where the ice cover seems to have been getting thicker and thicker and thicker, and then whammo, much, much, much thinner ice cover. And you might imagine that, you know, if the ice cover changes thickness, more sunlight is going to get through thinner ice. And so it's possible that we're going to see a response of the ecosystem to that change in ice cover in this environment. So we might want to plot up something like maybe the primary productivity, how much biological activity is actually going on, how much photosynthetic activity is going on, converting dissolved carbon dioxide in the lake into organic matter. So instead of plotting ice cover, we'll just plot up, for our inspection, we'll look at Isla Boni primary productivity in milligrams carbon per square meter per day. We, of course, don't want to maybe write all of that out in the label. So we'll call it Isla Boni, let's see, what should we call it? Primary productivity. And this can be, again, we can have the units here, milligrams carbon per meter squared. And, this is a case where, yes, you could use slashes for, per, but since there's a lot of them in there, it might be a little bit more clear. And then, of course, I'm going to make sure that those points are correct. So ELB, primary productivity. So our lake ice cover got thick and then thin. And what happened to our productivity? Oh, interesting. Our productivity kind of dropped and then got a little higher. Kind of cool. So, this is just a chance to peruse the data. And once you've made, one plot, you can kind of go through and look at everything. We have several data columns here, right? So there's soil invertebrates, things living in the soil, the Eurylimus and Scottnema. We have lake primary productivity in both east and west lobes of Lake Bonney. As you kind of go through, you'll see stream flow, you'll see microbial mat area or organic matter content. You'll see interesting information related to lake levels and ozone hole, soil temperatures. So it's a lot of data to look at here, and we'll go through this and make some plots of those data sets as we go through. But one thing that would be nice is, having made these 4 plots, kind of flip through them, you get a sense of how these things might be related, but really it would be best if we could see all of these together. So now what we want to do is see all our plots together as basically one figure. So it's going to be 2 rows and 2 columns. So to do that, we're going to use the parameter setting. And our parameter here is we're going to create a matrix of rows. It's going to be the MF row. And we're going to set that equal to a list of rows and columns, which is going to be 2 by 2. So that will then change up the plotting space to start accepting our plots. Instead of making a single plot in one window, we're going to put 4 plots in that one window. And we happen to have all of our plots there, right? So you've just made 4 plots. So you could go back if you really, really, really wanted to and plot up 4 different plots, or you could take your 4 plots and copy and paste them. So now what we've told R to do is, all right, so change that parameter and now draw those plots. So if we run our parameter function plus these 4 plots, let's make them one at a time just for fun. So now we have our air temperature plot in row 1, column 1. Then if we add in a new plot, we'll highlight that and run it. It adds in our solar radiation plot. So we have temperature and solar radiation. Then we've got our ice cover thickness, and finally, our primary productivity. Now, one thing you might notice is that this looks a little bit wonky, right? Air temperature, totally fine, solar radiation, totally fine. Our Isla Boni primary productivity in milligrams carbon per square meter per day is a little bit long, right? So we need to do something to fix that up. And so our Y label here is the problem, right? Our Y label here doesn't look great. So our Y label is just a little bit too long here. So instead of using our basic Y label function, we're going to add in a special command called string wrap, STRWRAP. And that's another function that's going to wrap that text. So when we run string rep, it takes in a string of text. It's a very long string. But then it says, okay, you know what? That's pretty long. So let's make it no more than 30 characters. So anytime you hit 30 characters, make a new line. So let's rerun. Now, if we just reran that, what would happen? It would create a new plot. And that's not quite what we want. Let's see, where's our error? We are missing, look at that, a parentheses, because we opened string wrap but didn't close it. So if we run that, what's going to happen? Well, it puts in our new plot in the top of our matrix of plots, right? Because we wanted to put in our all of our figures in a 2x2 row. So we're going to need to kind of run this from the top. So we can clear these away and clear the plots. And now, if we rerun it, what are we going to have? We're going to rerun it and see. So we'll set up our parameter 2x2 and rerun. All right, that's starting to look a little bit better. We're still running into this problem where we have a little bit of too much text crammed into this third line here. So maybe we should adjust that. And instead of doing a wrap on every 30 characters, we can make it every 35 characters. See if that buys us a little bit more room. So we'll rerun that. There we go. Looks pretty tidy. It looks pretty clear. So that's our first goal, right? We want to just get a sense of what our data sets look at like, and we have our data sets together. And we want to explore this relationship between air temperature, solar radiation, which is the big driver of air temperature in this cold desert, and then the ecosystem response to that change either in air temperature or solar radiation, something about how the lakes are changing and how life in those lakes might be changing. So once you've got your plots here, you might want to add in titles to them so that, you know, at a glance, you could look and say, okay, air temperature, solar radiation. So we do that with the main tag in your plot functions. And once you've got that, we want to start then looking for changes, and we'll do that in the next video. So looking at your plots of environmental change in the McMurdo Dry Valleys in Antarctica, one thing you might be wondering is there change over time? You know, what does climate change at this site look like? And one thing we might want to do is actually look and see, like, you know, is there some kind of linear trend with time? For example, in this case, is air temperature falling or is solar radiation increasing? Or, what's going on with this, ice cover thickness? And so a very basic test you might do to look for change over time in a data set is to try and fit a linear model to it. And this is sometimes called linear regression. This is an attempt to fit a line through your data, also called a line of best fit. And what linear regression is going to do is it's going to take all of your points in your data set and try and compute a line that minimizes the distance between those points and the line. So a line that, should change through time that was like way up here on this plot wouldn't be a very good line, right? Because all these data points are much too far from it. So that's obviously not the trend that this data set is showing. So how do we use R to calculate lines of best fit and therefore change? Well, we can use the linear model function. So we'll take our existing code and add in the search for change. We're going to look for a change in our data. And what we're going to do is we're going to compute a line of best fit. In this case, we might call this temperature best fit. And we'll define that as LM is the linear model. And linear model is a tool that takes in a x and a y, just like plot. And it takes in the y as a function of x, so it uses the exact same syntax as plot. You can either use x equals and y equals, or you can use y tilde x, y as a function of x. So let's look at, say, for example, McMurdo data, and we want to say, look at our temperature data. Here's our mean air temperature, tilde as a function of time. So we want to look for a change over time, and that's our data, our time series there. And so this will create an object called temperature best fit or temp best fit, which will show up in our environments window there as a list, interesting, of 12 things. So we're going to now look at this best fit model and get some information about it. So we can use the summary command summary of temp best fit. And when we run that, we'll get in our console window here some information. And so you may be familiar with the lines of best fit, or you may not be, and that's okay too. But really, two of the important things that we're going to get from this model, from this linear model, is a slope. So how is the say temperature changing over time, or how is solar radiation changing over time, and an intercept, and that's just the y-axis intercept. So it says, at our 0 value, what is the value, and how has that changed over time? And of course, for data that starts, in the 1980s, 0 is the year 0, and that's not very useful data, right? That's 2 centuries ago. What we maybe want to know about more is the slope. And so when you look at the summary of our best fit line, it's going to have an intercept value and its estimate and some measure of the uncertainty or error associated with that. And then a slope. And in this case, that slope has a slope of degrees per year, right? Because our data has a value of temperature in degrees Celsius, and our y-axis, or pardon me, our x-axis is in years. So it's this slope is degrees per year. So 47 degrees Celsius in Antarctica in the year 0 is probably not realistic, right? So one thing you always want to ask when you're doing a linear model is, what are the bounds of this data, and do those bounds make sense? In this case, the year 0 is not particularly interesting to us, although for someone doing paleoclimate, knowing about climate change over the last several thousand years is actually quite useful. For the moment, we're mostly concerned with the slope. And one thing we'll take a look at is sometimes called the p-value, and this is a measure of the statistical significance of the data. When you look at these p-values, one thing you'll want to see is that it's kind of like golf. Low values are considered better. So if there is actually a linear trend that connects these data points, it will have a low p-value. That's a low probability that the distribution of those points is random, and therefore a high probability that that temperature is changing as a function of time, for example, in this data set. So we can generate these linear models, not just for temperature, but really for all of our data sets. So why don't we just do that? And again, let's do just a little bit of cut and paste here. So remember, line 43 here, temperature best fit is what actually makes the model. And then summary lets us see it in the console. So we could make temperature best fit, and now we don't want temperature. Our next plot, so we have temperature, our next plot was solar radiation. So that could be like solar rad best fit. And again, all we need to do is change up in our command. We're going to take out temperature and put in our solar radiation. And now when we calculate that, we'll get a solar radiation best fit. We've also got our Isla Boni ice, so that might be Isla Boni ice thickness best fit. And we can just change that up. Again, we'll take out now temperature and put in Isla Boni ice thickness as a function of time. And we can make that object by highlighting it and running it. And we can do the same thing for primary productivity. So it'll be Isla Boni primary productivity best fit. Define that, and we'll just type it out this time for fun. Is linear model. It's our McMurdo data, Isla Boni primary productivity as a function of tilde our McMurdo data year. All right, so now we have these lines of best fit, but you might notice they're not actually on our plots, right? Because we've created a linear model, we've analyzed this data, but we haven't actually visualized it in any way. And so we certainly want to be able to visualize it. And so this is a case where, hey, why don't we just go and copy and paste our commands that make this nice group of 4 plots. So that was up here in our section where we said, see all our plots together as one figure. So you can grab all those graphical instructions. But we're looking for change in the data in this section. So one thing we want to do, here's our set parameters for a 2x2 column. Strictly speaking, we don't need to do that, right? Once that parameter is on, it's going to stay on until we turn it off. But it's nice just to have it to remind ourselves that that's what we're going to expect to see. But now what we want to do is add in that line of best fit to our data sets. So this is our first plot, right? We're plotting air temperature versus time in terms of the lines and the points. So what we want to do for this plot is add in that line of best fit that we calculated. Because the model, this temperature best fit is the calculation, we can actually show that line using the AB line command or ab line. This is a line that goes from A to B on a plot. And so by sticking it in right after the instructions to make the plot, add the points, now add the AB line, we can actually see this model on the plot. And so all we want to do is, this is just another command, just like points that add something to the plot. In this case, the thing that we're adding is our temperature best fit. So I typed part of it and then hit tab to get the rest of it out. And this is going to add a line using that linear model. And we want to see, we want to make it, maybe we'll make it a dashed line. So line type equals 2, and we'll give it a color, just so it sort of stands out a little bit. Oh, maybe we'll make it red. So now, if we run those commands, we have now cleared our workspace, made a 2x2 grid. Now we're plotting temperature, and look at that. That is our line of best fit going through the temperature data. So we can do this exact same thing for each of our plots. And again, just copy that ab line command, and we can stick it in after each of our plotting commands. So now instead of temperature best fit, this line 58 plots our solar radiation. So that's our solar radiation best fit. So we can just change that out. This next is our Isla-Bani best fit. So that's a Isla-Bani ice best fit. We'll stick that in. And then finally, here at the end, we will have our linear model for Isla-Bani, and now we have our primary productivity PP best fit. So we've run one of these plots, right? That was our temperature plot. We just want to now run the remaining 3. And so when we run them, look at that. We have got our 4 plots again, but now we've got them processed in a way that we can see change over time, which is interesting. For that temperature plot, your eye sort of follows that line down, but there's certainly some complexity to it. For the insolation plot over on the right, maybe that there's an increasing trend with time. But you look at these lines and you look at that p-value that we looked at in the summary before, and they're just not great. And so one thing we might want to do is think about, one of the assumptions of a linear model is that across our whole data set, across our whole time record, there really is linear change with time, that every year there's an increment down, certainly with some variability or some other competing factors, but a linear model sort of assumes linear change with time. But maybe that's not what's going on here. Maybe there is one or more linear changes with time happening, and we want to sort of figure out where that's happening. And so that's what we'll look at in the next video. So one thing we might want to do is look to see if we can explain these not so great linear fits to our data by breaking our data into one or more sub-data sets, see if there are more than one linear fit that might describe this data. And so if we're going to do that, we want to look for a natural break in the data that might show a difference in trend or difference in time. So we'll put in a comment here to look for breakpoints in the data, look for breakpoints. And to do that, we'll use the plots that we've created, which have those excellent, interesting fit lines on them. So what we can do is we can just copy those 4 plots. We'll just grab that part of the script again, put it down here. And now what we want to do is not just make those plots again. We want to make a plot, for example, of temperature versus time. And we want to show the data, and we want to show the best fit line for it. But we also want to add in some grid lines. And so one thing we might do is just put in another AB line, another ab line. And what we'll do is drop in the vertical line. So V in ab line means put in a vertical line equals, and we'll use the McMurdo data, and we'll just use the year, right? So when we do that, one thing, what'll happen is our first plot will now have these really kind of gross looking vertical lines. And these are basically chart junk. We might think about maybe not using solid lines. We might switch around that to make a, for example, a dashed line here. Let's see how that looks. Oh, that looks a little bit better. All right, so let's clear this workspace again, and make sure that we are going to see all of our plots together. So we'll set that parameter to 2 by 2. And now when we make that plot, there we go. We've got some dashed lines to look for some natural breakpoints. So all we'll need to do is copy this command, the ab line, within those vertical lines at every year, into each of our plots. So now let's add this in at the end of each of our plots here. And when we run those remaining 3 plots, this should populate. So we've got our air temperature, our solar radiation, our Bonnie ice cover thickness, and our Bonnie primary productivity. And we can start looking to see if maybe there is a breakpoint in that data. And it looks to me like there might be a breakpoint in our data sets somewhere around the 2000 to 2001 or 2002 field year. This is where our temperature record kind of bottoms out, and then it's kind of flat after that. Again, looking at that sort of 2000, 2001 field year, we have increasing solar radiation and then kind of flattening out after that. In our ice cover thickness data, we have sort of increasing ice cover up until about, again, sort of that 2001, 2002 field year, and then perhaps a decreasing trend after that. And again, sort of a break point around the 2001, 2002 year where primary productivity is decreasing at Lake Bonnie. And that's it's decreasing as that ice cover thickness increases. And then it sort of flattens out or rises up a little bit as the ice cover thins again. So if we want to break our data sets using these natural breakpoints, we can go back to our original data sets, right? Our McMurdo data table that we've created, and actually split it into a couple of pieces. So let's make a note to do that. So we'll now split our data. And to do that, we'll create 2 data sets. We'll create a before data set, which is just one that's the early part of the record. And so what we'll do is we'll index the McMurdo data set. So we have our data set here. And to index it, we're going to use square brackets. And that means we're going to pull out certain rows and certain columns. And so what we're telling R to do now is to take the McMurdo data, and we want a certain number of rows, and then we want all of the columns of data. And so the rows that we want here are the rows for which the McMurdo data year is less than 2002. So this will be all of the years up to 2001. And then we want all of the columns of data. Before I run this line, let's make the after line. So our after data set is going to be the same thing. It's going to be the McMurdo data, and we're going to index it again such that we want all of the rows for which the year is greater than 2001. So this will be, before will be 2001 and prior, and then after will be 2002 and later, right? Because these are non-inclusive greater than or equal than. So this is everything less than 2002, and this is everything greater than 2001. So when we run that, here's what we've got. Our McMurdo data, right, was 26 observations. That means 26 rows of data of 21 different variables. Our before data set is 14. Oh, how about we get an error? Undefined, undefined column selected. So if you don't add a comma there, of course, it doesn't know that you want those columns. All right, so we had 26 observations originally. In our before data set, we have 14. In our after, we have 12. 12 plus 14 equals 26. So we've now split our data into 2. So now our goal is to replicate our plots, but now with our split before and after data. and to apply best fit lines to the before early part of the data set and the later after part of the data set. Before we actually make the graphs, I'd like to make the linear models for us first. And so these are going to be very similar to the best fit lines that we made for the whole data set. We're just going to do them for the before and after part of the data set. So for example, our temperature best fit data, we can have temperature best fit, and that'll be for the before data set. And this is going to just be a linear model again of our before data and temperature. So that's our y data as a function of tilde our x, which is before, and we want year. So that is going to produce a linear model just for the temperature of the first part of the data set. While doing that, let's make the after at the same time, just so that it's tidy, so we can copy and paste that. So again, the only thing we're changing here is which data set we're looking at, which data frame. So we're looking at after here, we're looking at after here. And this is important, right? Because the years are different. And so we want to make sure that the years line up. We don't want to be looking at, 1988 to 2001 as the x coordinates for the after data. We want to be looking at the appropriate bits of time. So now we can run those. That'll create the linear model. And now let's see what that looks like. We'll use the summary command to look at for example, let's look at the before first. So now when we look at that, what do we see? Well, we have our intercept, that's our y value, and our slope of cooling in the first part of the data set. And this is our slope, about cooling about 0.1 degree per year. And in our significance codes, this is R's way of telling us whether these are statistically significant fits. And the threshold for statistical significance in most scientific publishing is around 0.5, that 5% chance that this is a random distribution, or these data are drawn from a random distribution. And so, our before trend, that cooling trend is marginally significant. That's what this little dot here means, as it's sort of marginally significant. What about our after? So we'll look at, we'll use the summary command. Now we'll look at temperature best fit after. And we run that. What do we see? Well, a really flat trend, right? And then after data set, basically no cooling at all, maybe 1/100th of a degree per year. We practically couldn't measure that in the field. But this is what it's describing is that slow cooling trend up until about the year 2000, and then a flat temperature trend since then. And this is something that's referenced in the articles that you were reading, and is a phenomenon that folks really struggled to explain in terms of the local impacts of climate change on the dry valleys and the ecosystem response to that. And this slow turning around of that cooling trend and working back towards warming. So we can use copy and paste now to make these best fit lines for our other data sets. So we want them not just for temperature, but we also want our solar radiation. So that can be solar rad best fit before. And so what do we need to change? Well, we're looking at the before data set. And now what we want is not the temperature, but we want the mean insolation as a function of time. Solar radiation, solar rad best fit after is, again, all we have to do is change up the solar radiation. And now we could look at solar radiation best fit before. Oh, looks like it has, there we go. And solar rad best fit after. So now when we run those, what do we see? Well, this is interesting, right? This is our solar radiation best fit before, and that's the part of the line here that's the increasing trend here. And sure enough, what we're seeing in this data set is about 3 watts per meter squared increase per year. And the p-value here, our significance value, is nice and low. This is a statistically significant increase in solar radiation. And then what do we see in the after data set? What we see is that solar radiation is pretty flat, less than a watt per meter squared change per year. It's pretty noisy. There's not a significant trend here. So let's keep making these lines for our other data sets. So we did temperature, we did solar radiation. Now we need our East Lobe Bonnie, so ELB, and then ice, best fit before. And so we'll change that to no longer watts per meter square, but East Lobe Bonnie ice thickness. And then East Lobe Bonnie ice, we can just delete out our solar radiation and paste in ELB ice. Then that's our after data set, and we want that to be East Lobe Bonnie ice thickness. And we don't need to look at the summaries here. You can certainly look at that if you want to, but don't let it get in the way of making these data sets. So our last best fit line we want to make is now the East Lobe Bonnie primary productivity. So instead of ice, ELB, or ELBPP, best fit, that's going to be East Lobe Bonnie primary productivity. And same thing here, East Lobe Bonnie primary productivity, best fit, run it in our after data set. And there it is. So one thing to be mindful of is that we don't want to be accused of p hacking, and this is a term that's used for people who try and slice and dice data sets into smaller and smaller and smaller groups until they find a statistically significant finding. So for example, if you had a big epidemiological data set, you wanted to know whether people washing their hands prevented certain virus or bacterial transmissible diseases, you would probably find a pretty robust finding that people wash their hands more have a lower incidence of that disease. But if it was a more esoteric kind of variable you were looking for, and you didn't find that value, one thing that unscrupulous researchers might do is start slicing and dicing that data set into smaller pieces and say, well, what about people who wash their hands only on Tuesdays? What about men who only wash their hands on Tuesdays? What about men between the ages of 15 and 64 who wash their hands only on Tuesdays? And so as you produce a smaller and smaller data set, it may be that you produce what appears to be a more statistically significant result because that p-value changes, but it's not necessarily going to produce a more realistic or accurate finding. All right, so we've got our data sets, we've made our lines, our best fit models. Let's actually see how they look and compare to these plots that we've been looking at. So now what we want to do is make our before and after plots. And we're gonna make them one at a time. So we're gonna switch our parameter over to our rows now are equal to 1, 1. So we want to make just a single plot at a time. So when we make our new plots here, we'll see them all at once. What we could do is put our parameter here for our rows for 2 by 2 when we want to see them all together. We have that commented out here, so we can turn that back on just by uncommenting it out. So what are we going to do? Well, first thing we're going to do is make a plot of our before data. So we're going to look at our before, and we want to look at our summertime temperature on the y-axis as a function of our x-axis, which is our before year, right? It's going to be a line type, so type equals line. And let's see what else. Line type is 1. That's a nice solid line. What else are we going to do? So our x labels, here. These are basically the same plots we were making before, right? And this is going to be mean December, January, February, air temperature, option K, degrees C. Now, here's one thing to be mindful of. The x limits for this plot, we could make them the whole time range of the data set, right? 1998 to 2014. But if we did that, that's what we need to do, right? We need to make sure the plot has the full data set. If we just plotted the before data without setting this x limit, it would only plot the before data as a subset of the plot. And then if we tried to plot the after data on the same plot, it would be cut off. We actually wouldn't see it. So we need to explicitly tell R that we want to have that full data range. So we're going to set the x limits to a list of years here from 1988 to 2013. Y limit we can set to if we want to. And let's make sure again that we can use the full range. Because what if the temperatures were colder in the first part of the data set and warmer in the second part? Well, if the y-axis is set by the first data set that we add in, we run the risk of cutting it off. And so we want to make sure we don't cut that off. So we're going to set the y limit equal to a list of numbers, and that list of numbers is going to be derived from a function. It's going to be the minimum value of the whole McMurdo data set air temperature record. Then outside of that, so that was our minimum. So that's the low value. Now we want to look, the high value for our y-axis is going to be the maximum of that whole data set temperature record. All right, 1, 2, 3, close. So that should now, when we, very nice, when we run that, it makes one plot, a single plot. And as you can see, it's just the before part of the data, but it uses the entire X range. So when we add in our after data, we can add that in. So of course, what do we want to do? We want to make this plot look pretty. So we'll add in the actual data points, just as we've done before, using the points command. So that'll be the points data. And we'll use the temperature data. That's our y as a function of our before data. And years are our x. And we'll use our standard point character of 20 just to make it look pretty. All right, so now we have points on all of those years, showing where our actual data are. So now if we want to add in our after data, how are we going to do it? Well, we're just going to use the lines and points commands, right? These are two commands that add line or point data to a plot. So if we want to add in our after data, we can use the lines command. And when we do that, what we're going to add is y data, which is after, and it's going to be the temperature data. That's on the y-axis as a function of after years on the x-axis. So this will be our temperature as a function of time in the after data set. And we can make this look just like the first data set by setting the line type equals to 1. So when we run that line, now we've got our after data added in. We want to put some points on there. So we'll use the point tool, the points command again. And this is going to be, we can actually just copy and paste it, right? Why not? Save some time. So this is our after temperature data. And just to make it look just like the first one, we'll use point character of 20. So now we've got that data. And now we want to add in our best fit lines that you've made for the before and the after data. And to do that, we're actually going to use a tool which is not part of BaseR, but it's part of the Plottrix library that you installed. And it's called AB line clip. And what this does is, if we didn't use this command, our AB line for the first part of the data set would continue all the way down like that. But we don't think that that best fit line is describing data after 2001. We think we have a different line after 2001 that describes that data. So the AB line clip lets us define where it is that we want to have that best fit line show up. So what we want to add first is the temperature best fit line. And in particular, what we want is the temperature best fit before. That's going to be the first line. We decided we were using a nice dashed line for that. So line type equals 2, color equals red. And let's see. And now we can use the AB line clip to prescribe the X range. So on the X axis, where that line is going to go. So here, X1, our starting point, is going to be equal to 1988, the first part of our data set. And X2, the end of that line, is going to be 2001, which is the end of the before data set. So now when we add that in, beautiful. Now we have a best fit line for that earlier part of the data set. You can imagine what we're going to do, copy and paste, right? Now we're going to do the temperature best fit after. Line type is 2, color equals red. And now we want this to go from 2002, the start of the after data set, to 2013, the end of the after data set. Very nice. So you can see that really strong cooling trend in the early part of the record, and then a real flattening out of that cooling trend in the second part of the record. So just like we've been doing all module now, we have a template for what it is we want to create. And so we might as well just use that template and copy and paste, right? So here, this is going to be a little bit of just sort of detailed work of copying and pasting out, right? Because we have our temperature plot. That means we can make our solar radiation plot. We can make our Isla-Bani ice thickness and primary productivity plot just by duplicating these 4 plot commands and changing what's on the y-axis, because the x-axis is fundamentally always the same, right? It's always the before or after years. So I'm going to pause the video here, let you do that, and then we'll get together for maybe 1 or 2 more videos to put all this together at the end. So one thing that we've been talking about over the course of this module is the idea that there might be environmental variables that are related to each other. You know, that we might see, for example, thickening of ice in Isla-Bani and then a decrease in primary productivity at the same time. And then when the ice thickness decreases and more light gets through, then primary productivity increases. And we suggested that maybe this could even be potentially related to the fact that solar radiation was, low at the early part of the record, and as solar radiation began to increase, perhaps that triggered some kind of thinning of the ice, reached some threshold where that ice began to thin again. And so one thing we might want to do is actually try to test some of these correlations and see whether data sets might be connected in some way. So what we're going to do in the last bit of this module is look for correlations between our data sets. Our data. We'll look at one correlation, and then your challenge is to potentially find some more. So we're going to leave behind our group plots here for a moment that have kind of given us this idea that some of the data sets might be related. And we're going to just plot plots one at a time so we can kind of see them all together, but we're going to plot the data instead of next to each other, actually overlaying the data on top of each other. So we'll set up a new set of parameters. We'll set up our margins here. And remember, those margins are bottom left, top right. So we have still lots of room to work. On the bottom left, on the top, we don't need quite so much. And on the right, we do want a fair amount of room. And so let's go grab from the very beginning of our record here. We plotted up our data of Isla-Bani ice thickness. So we can grab that Isla-Bani ice thickness data set. Let's see, where is that? Ice thickness is right here for us. So we can grab that plot, and now if we'll set our parameters. That's, we may need to, oh, look at that. We need to reset our parameters to just plot one at a time. So if you've forgotten how to do that right, we can grab our MF4O parameter from earlier and now put it up here. So now we'll say, just make one at a time, give us nice big margins. Perfect. All right, so we have ice cover thickness, and then we have year. And one thing we want to do is now say, you know what, we want to plot over top of this our Isla-Bani primary productivity data. And so we'll put in a new graphical parameter here. And that parameter is new equals true. And so what this is going to do is it's going to give us a new plot over top of this one. So we can actually go up and grab, if we want, our Isla-Bani ice thickness data. And we're about to now, or pardon me, our Isla-Bani primary productivity data. And one thing we're about to do here is plot over one graph with a new graph. And if we do that, there's a real distinct possibility that we're not going to be able to tell one from the other, right? Because it's a black line with black dots. So why don't we go back to our Isla-Bani ice thickness data and add in some color, right? Color equals, I guess this is ice, so maybe we want it to be blue. So we can do that for both the lines and the points. Color equals blue. So we'll make that. And now we have a nice blue plot for our ice thickness. And here, this is biology. So let's make the color equals to green for both the line and the points. And when we run that, we should get our primary productivity data and our ice thickness data. But of course, one thing you noticed is this looks pretty gross, right? Because we're trying to make two plots using a y-axis over on the left side of the plot. And they're overprinting on each other. So that's no good. We want to fix that. And so, of course, we can do that by suppressing the second graph's y-axis labels, right? They have the exact same x-axis labels. It's just our years. But we want to tell it, hey, don't overprint primary productivity over our ice thickness data. So in our plot where we plot primary productivity, just after we told it color equals green, one thing we can do is tell it axes equals false. And that's then says, hey, don't plot axes on here. And also don't plot labels, right? Don't plot X labels or Y labels. So we can write X label, X lab equals nothing, Y lab equals nothing. So that's this little empty quotation marks there. So when we do that, that should suppress drawing the axes on. So if we rerun these plots together, there we've got, let's see. Why does it produce an error there? Let's see. So false X label equals nothing, Y label equals nothing. What's going on there? Is matched by multiple arguments. Oh, look at that. So it's trying to tell us that we have already tried to tell that our X label is year here and our Y label is primary productivity. And of course, it says you can't make more than one label. So we better delete that out. So now, all right, now we have our ice thickness in blue, our primary productivity in green. But of course, we want to add the actual label so we can know whether ice thickness and primary productivity correlate. So the one thing we'll need to do now is add in an axis. And this axis is going to be axis ticks and labels. And the side is going to be 4, because we remember position 1 is bottom, then 2 is left, 3 is top, 4 is right. And at is where the ticks are. And what we're going to have it do is we're going to put them in, we're going to use a command called pretty, which is going to take in data, and particularly it's going to take in the range, that means sort of the minimum and the maximum of our McMurdo data. And what are we trying to plot here? Of course, it's our Isla-Boni primary productivity data. We're going to remind it to remove missing values, right? So if there's no data there, you can remove them and you don't have to count them in the range. So any RM is true. What that's going to do is say it's going to take axes and calculate sort of what are the natural breaks in the range of this data set. So now when we run that axis command, it gives us our range of primary productivity values in nice even breaks. In this case, it said, counting by 2 seems to make a lot of sense. And now we need to add in a label, right? What are these units of? So we can use the mtext tool. This will add in text. And it's going to add in our label, East Lobe Lake Bonnie primary productivity in milligrams of carbon per square meter per day. Where is it going to put that text? It's going to put it on side equals 4. And where is it going to put it? It's going to put it on the second line, kind of down on that side to give us a little bit of room so it doesn't overprint those numbers. Line equals 2. That looks pretty good. If you think that's crunched, you could put it on line equals 3. Anyway, would be totally fine. All right. Last thing we probably want to do is add in a legend, right? so that we can remember, hey, what's blue, what's green. So to do that, we'll use the legend command. And the legend, we are going to put it in the top left because you might notice that there's a lot of space up here, so there's plenty of room to put it. And the text is going to be a series of entries. One of them is going to be ELB ice. So we better put that in quotation marks because it's ice thickness. And then the other could be ELB primary productivity. The symbols we're going to use, that's our point character, is going to be dots for 20. The line type is going to be 1, right, because we have straight lines. And then the colors are going to be, if ice comes first and primary productivity comes second, then the ice should be, the color should be a list of things in text. So ice was in blue and primary productivity is in green. So there we have our plot now, which we can begin to compare ice thickness to primary productivity. And, you know, to my mind, these look pretty related, right? When ice thickness goes up, primary productivity drops down. When ice thickness drops, primary productivity rises up again. So, you know, we want to now take a look at the data and see, are these things really correlated? Can we say that there's a relationship between any given year's ice thickness and any given year's primary productivity? Now, that's a really good question. So let's not note it down in our notes. Are these data sets correlated? So to answer this question, are these data sets correlated? We better figure out a way to just look at the Isla-Bani thickness data. So let's make a new data set, which will be Isla-Bani data. And that's going to be just a subset of our McMurdo data, right? Because our McMurdo data has, you know, average air temperature, it has nematodes, it has all this good stuff. But what we really want is Isla-Bani ice thickness, which is column 8, and Isla-Bani primary productivity, which is column 10. So we can just parse that data out and say, we want just the McMurdo data, and we're going to index again. We're going to index it for all of the rows of data, but we only want columns in our list here, and our columns are going to, the list is going to be column 8 and column 10. So now when we run that, we have ELB data, which is now 26 observations, right? It's all the years. But a couple things are going on here. One, we don't have the years, right? We didn't pull that out as a data set. Do we need them? Well, no, right? Because we want to know not are these correlated over time, we want to know are these correlated absolutely with each other. So year in and year out, in each entry, does the ice thickness correlate in some meaningful way with the primary productivity? The other problem that we might face is that there are some years where we have no data, right, in any of them. There are some years where we have data in one column, but not in the other column. So we need to make sure that we go through here and only look at data where we can correlate 1 year's ice thickness with its primary productivity. So to do that, what we'll do is we'll go through and redefine our Isla-Bani data now that it exists as the Isla-Bani data, but we only want the rows that are complete cases. So complete.cases is a command that will say, look across each row, and if there's any missing data, any NAs, and not availables, throw that one out. So it'll be, we want rows that are complete cases, and we want all of the columns. So right now we have 26 observations of our 2 variables. Now when we run this, we've thrown away the 1, 2, 3, 4, 5, 6 years where we don't have complete cases, right? Where there's some data set missing. Usually it's the ice thickness data that's missing. And so we just want to get rid of those. So now we can start plotting this data and making a linear model for it to see if these data sets are actually correlated. So we'll make a new plot. And this is going to be not a time series plot. It's going to be a different kind of plot. So just to kind of get used to thinking about it in a slightly different way, instead of having years that are the x, we're going to say the x variable is going to be our Isla-Bani data. And let's look at ice thickness. So we said this is sort of our driving variable. This is the thing that we think might be controlling primary productivity. Then our y values are going to be our Isla-Bani data, and we're going to look at the primary productivity. And let's see, we better put some labels on here. So our x label is not years again, but now it'll be ice thickness in meters. And then our y labels, of course, our Isla-Bani primary productivity in milligrams carbon per square meter per day. All right. And just so it looks pretty, we don't want this to be a line plot, right? We want this to be points, because unlike our plot here that shows change in these values over time, we don't think that we're necessarily going to see a continuous series of events. We're going to see every year, we want to know where its data fit in our space here of primary productivity and ice thickness. So we'll make sure that it's a point plot. And so we'll use our point type, our point character of 20 there. So now let's make this new plot. So when we do this, here's what we got. We have basically a scatter plot where we say for a given ice thickness, what's the primary productivity that emerges from that? And I tell you, this looks kind of correlated, right? When ice thickness is low, primary productivity is high. When ice thickness is high, primary productivity is low. But we can test this, right, using our linear model, because our linear model, our linear regression, is a way of looking for correlation with the data and some kind of rule or mathematical law that governs the relationship between those data sets. So we can do an Isla-Bani best fit ice PP, that's the name of the object. And what's it going to be? It's going to be a linear model that relates the Isla-Bani, let's see, Isla-Bani data. And we want to relate now y is a function of x, right? So we're going to do Isla-Bani primary productivity as a function of Isla-Bani data, Isla-Bani ice thickness. And that will be our linear model, so we can calculate that. And now we can, let's take a look at it actually. Let's see what's going on. So summary, Isla-Bani best fit, ice PP. Well, here we go. So what do we have? Well, what we've got is a model that has an intercept, right? That basically if the ice thickness went down to 0, we might expect 26 milligrams of carbon per square meter per day to be produced. That's what this value means. And that's highly significant based on the linear regression model's output. And as we increase in ice thickness, this negative value suggests that our Isla-Bani primary productivity decreases by about 2 to 3 milligrams of carbon per square meter per day for every increased meter of ice. And again, this little dot here means we're just on the edge sort of significance to marginally significant. So this is actually a pretty good correlation for ecosystem data. Let's show it on the plot. So let's put the AB line in, and the AB line there is going to be our Isla-Bani best fit model. And let's make it a nice looking dashed line. So line type equals 2 and color equals red. So it looks nice. So there you have it. There is our decreasing trend in primary productivity in this ice-covered lake ecosystem as ice cover increases. So basically, we're now at a point where we can explain what's going on with primary productivity in this ecosystem as a function of environmental variables. And so the question that I want to leave you with is, what else might be correlated? What else might be correlated in the McMurdo long-term ecological research data set? And so your challenge for the extension here is to look through the MCM data and use the tools that we've generated for generating multiple plots, plus or minus with breakpoints in them, and to look for correlations between some of our variables, right? So our invertebrates, the Scottnema and Neutera limus, between things going on in East Labani or West Labani. Um, we've got light coming in, we've got stream flow coming into lakes. We've got algae, Formidium and nostoc living in the streams. We've got lake level, we've got the local ozone hole value. We've got interesting data about soil, we've got chlorophyll. So there's tons of choices here. And the question for you is, what else is at work in this ecosystem and how can we understand it? And I hope you enjoy the challenge.